So yeah, hello. Let's start to solve some exercises, some simple exercises on week 12. Okay, so here we have first question. Uh, L over K finite separable field extension, which is not normal, and let N be normal closure of L, so that Galois group of N over K, this field extension, which is now Galois extension, is non-abelian. Okay, so what it is, let me write here. L over K is finite and separable extension, but not normal. So now we take field extension N over L over K such that N is normal closure. So okay, how should we write it? It is finite separable field extension. So first of all, what is N? Here we have question mark for time being. What I want to do here is this: since L over K is finite separable, is finite and separable, we'll see that L is of this form. L is isomorphic to some K alpha or some alpha, right? It is simple field extension. This is primitive element theorem. Now consider mu alpha K belonging to Kx monic irreducible monic minimal polynomial, or we should write just minimal polynomial. Okay, it is understood that we can take minimal polynomial for of alpha. Now we want to attach all its roots inside L. Then we say that uh, then what is N? N is nothing but L attached with all the roots of this mu alpha K. Okay, in some algebraic, let's say K closure, we attach this finite set of roots inside L, we get uh, normal closure. Now N is nothing but a splitting field of, sorry, now what is happening? N is nothing but a splitting field and a splitting field of mu alpha, which is so this is Galois extension. This implies N over K is Galois extension. Now what they mean Okay, here now it is Galois extension. If Galois n over k is abelian, then in abelian group all its subgroups are normal, right? And note that whenever this is Galois, this is always Galois. Now this is this Galois or not? Is question mark, right? So what to do then? We just see here, then all its subgroups are normal. Normal. And what happens in this case is this n over L is always Galois, no matter what this Galois group n is n over k is. But this L over k is Galois if the corresponding subgroup is normal inside Galois group, bigger Galois group. Okay. In this case, but this is Galois extension, since Galois L over k or n over k is abelian. Okay, so let's see now what uh, yeah, this is Galois extension, this is Galois in this case. So Galois, but Galois extensions are normal and separable. Separable we don't need, but this is contradiction. Okay, contradictions to what? L over k is not normal. Okay, so this is how we how see. Uh, okay, this I think this was done in previous weeks. We say 8th or 9th week, that when this extension is Galois. Okay, so in the Galois correspondence, this follows that if normal subgroups correspond to uh, Galois extensions. Okay, so normal subgroups correspond to Galois extension, and any other subgroup correspond to, okay, all the subgroups correspond to some intermediary fields, but only those groups which are normal gives uh, Galois extensions. Okay, so Galois correspondence for you, I can recall it here. Uh, One side we have fields, here we have groups. For any field extension, let's say as given here, N over K, Galois field extension. Then here we have this Galois group, automorphism group of N. K algebra automorphisms. And what is, and any subgroup here in this case gives an intermediary field. Okay. For example, if let's say we have H subgroup of, let we call it G here, then uh, this goes to fixed field of N fixed by H. This is field between N and K. And where any field, intermediary field goes, let's say K. In the middle we have, let's say, F. Then we know that N over F is Galois, so we'll send this to Galois N over F. This is subgroup of Galois N over K. Okay. Good. Anyway, this was Galois correspondence. It is one-to-one correspondence between subgroups of Galois group and intermediary fields of N over K. And now here, if subgroup is normal, then this field in the middle, this extension is also Galois. Okay. Okay. So let's see. Next question. Okay, so the next question is about a polynomial in Kx of degree n, whose Galois group is symmetric group Sn, so that any splitting field of Fx cannot be generated by fewer than n minus 1 zeros of F. Okay, so first of all, let's say we have this zeros of F be in some splitting field. Uh, let L be splitting field of F over K, and let we denote zeros of it is not, let VF inside L, all the zeros we are writing x1, x2, x3, and so on xn. Note that if F is not separable, uh, this set might have cardinality less than n. Okay, because while writing two elements they are same, then we'll remove one of them. So here it is not given that F is separable or not, but let's see, if F is generated by, let's say, fewer than n, means, let's say, let and assume, if possible, uh, let L generated by n minus 2 elements. Let L be generated by n minus 2 zeros of F over K as fields over K. Okay, so as field over K, then and without loss of geometry, assume that. So after some maybe uh, permutation of roots, you just assume that L is equal to K. We are just testing these elements x1, x2, xn minus 2. Okay. Now, if you just get intermediary fields here like this, L over K x1, x2, xn minus 3. Next, we have K x1, x2, xn minus 4, and so on, going down. What? K x1, x2 here, and more below we have K just x1. Now we have K. So these intermediary fields, this is nothing but K x1, x2, and so on xn minus 2. This is if possible. Okay, so we might get some contradiction. Uh, okay, so what we have this. Let me change the color. We have uh, L L is F L is a splitting field of K. Sorry, a splitting field of F. And what is Galois group of F? This is nothing but yeah. So we have we have this Galois group of F over K. This is defined by Galois L over K, where L is a splitting field. L is splitting of I splitting field of. They are all splitting field up to I. There is some isomorphism, so we can write I is just a splitting field. Anyway, L is a splitting field of F. We consider the Galois group of L over K, and so what is cardinality of this is, let's say, cardinality of Galois group L over K, and its splitting fields are Galois extensions. So we also have here L over K degree, and this is nothing but cardinality of Sn, right? Because Sn is the Galois group of F, and this is nothing but n factorial. Good. So the degree between this bigger degree is n factorial. Now, if you see what will happen to this degree. Okay. So what is this degree? Kx1 over K. This is less than or equal to n, right? Why? This is just because x1 is root of f, and okay, since x1 belongs to vf, okay, and so mu x1 k divides f. This implies uh, degree of mu x1 k, this is less than equal to degree of f, and this is less than this is just exactly n, sorry, and this degree is nothing but this degree of extension, right? This is this is we are doing from maybe second week. We are using always simple field extensions. Their degree of extension is nothing but degree of the minimal polynomial of that primitive element. Okay, so this is this degree of extension I'm writing here is less than n. Now what happens to this degree of extension? So I'm doing once more, but again we'll just write it by induction happens like that. So what happens to this degree of extension? Degree of k x1 x2 over k x1. What is this? Or what is bound for this extension? Okay. Now this is, if you see, this is also simple field extension with primitive element just x2, right? This can be written like this: kx1 with just attaching one element, which is x2. So x2 is primitive element. So we'll just see what is minimal polynomial for x2. Okay, so because x1 x2 both are roots of f, so x2 is root of, since x2 belongs to vf, mu x2 kx1, whatever it is, it will divide f. Okay, and now f can be written as x minus x1, which is already inside kx1, into some g, right? Because now x minus x1 is not root of not participating in this minimal polynomial, right? Okay, so mu x2 is coming from these factors. Okay, so I hope you understand here. So in this factorization, x minus x1 is not a factor here. So uh, this divides something which is lying in this factorization of g. Okay, okay, good. So what happens here? What is this implies that mu x2 k mu x2 k x1, this divides g, where degree of g is exactly n minus 1. So in particular, this implies that this Galois extension, sorry, this extension x1 x2, I'm writing round bracket or square bracket. They are same because these are algebraic elements anyway. Okay, so by if this is my fault, I should not write round bracket. Oh, sorry, not square bracket. K, I should write round bracket only. All bracket x1. This degree of extension is nothing but degree of mu x2 k x1, but this degree is less than or equal to degree of g, which is actually n minus 1. So this is less than n minus 1. Okay, so this is how it is happening. In each step, it is the case. Every time this degree of extension is less than or equal to. So what is the relation between them? This one is n, and then n minus 1, n minus 2, n minus 3. So this is less than or equal to 3, right? Okay, so what is total this is contradiction, right? So writing this way, n factorial, which is equal to L over K, and writing L over K x1, x2 up to xn minus 3, this into K x1, x2, x minus 3, n minus 3 over K x1, x2, xn minus 4, and so on, writing this way. And lastly, we have this K x1 over K. This this is this is less than or equal to 3 into 4 into 5 into and so on up to n, and this is nothing but n factorial by 2, and this is contradiction. Okay, so I hope you understood here. So whatever the problem here is uh, to understand why this divides f, and then why it should divide g only, not x minus. So the irreducible polynomial, it is prime, so either it will divide x minus x1. Okay, let me tell you this. Since this is irreducible, has no extra fact irreducible, it should either divide this or divide this. And now because x minus x1 is if it divides, so here we have these are distinct. Okay, I'm just assuming that they are distinct. Okay, uh, assume. So here the big assumption should be, I'm just assuming, assume f is separable. Okay, or if it is not or less, we can assume that up to at least x1, x2, and so on, xn minus 2 at least, at least these are distinct roots, are distinct roots of it. So in this case, what we have here, that if it divides this, then x1 and x2 must be same. Okay, but because x1 x2 are different, so this irreducible polynomial mu x2 so divides g only. Okay, okay, good. So I hope you understood this. Once it divides g, its degree should be less than or equal to n minus 1 because g is of degree n minus 1. Okay, cool. So for next, I'm not doing them. This is, let's say, A1 step. This is A2 step. Similarly, A3, A4, AN minus 2 steps. Uh, Let me write this as a star. Okay, star is this that the degree of extension corresponding is they are less than or equal to, this is less than or equal to 4, and so okay, good. This question is done. Let's see next part. Here we have okay, this is okay. Let's see. Fxb reducible polynomial of degree p, that's p is prime. Let kf be splitting field of f over k. Then what happens? Furthermore, for intermediate subfield, we want to show that fx is still irreducible inside E when sorry, if and only if p is divide, p does not divide E. Okay, first let write this diagram here first. Here we have k f splitting field of and E is intermediary field, and here we have k. Okay, now let's see how we can do this. Mhm. If something is root of f, we just attach into E. Let start with this. Uh, Let alpha belonging to kf be a root of f. Then okay, sorry. What happens to attaching? I'm just attaching alpha. So round bracket, square bracket, they are same because alpha is algebraic. Okay, so no matter. So it is not the. So here we have E, and let me write this kind of diagram. Somewhere here K alpha is over K. This is so in this lattice diagram, if you see E alpha over K alpha, on we have two paths from E alpha to K. Okay, so what will be the degree of extensions here? E alpha, let me write down back. E alpha over E, then E over K. This index is equal to E alpha over K alpha, then K alpha over K. So what is degree of extension K alpha over K? Right? Because F is in Kx, F belongs to Kx. And what about if F is irreducible and yeah, F is irreducible and prime degree. So what should be this degree? This is degree P, okay? Because degree, what is minimal polynomial for alpha? It is just Fx, okay, nothing else. Because F satisfies alpha and F is irreducible also. Any irreducible polynomial which satisfies F of lower degree will be minimal, but lower degree than F, they will not be factor of F because F is itself irreducible. So alpha is had minimal polynomial just F, and so K alpha over A, this will be of degree extension K, sorry P. Now, okay, so if we what E P does not divide K if we assume, so let's say if you assume that P does not divide E over K, this X field, this degree of extension, then what we conclude from here, P divides E alpha over E, this degree of extension. Okay. But this is simple extension. So uh, P divides degree of mu alpha E, right? What else do we have this here? That also, and since F belongs to E X and F of alpha is equal to also 0, this implies mu alpha E, which is minimally reducible polynomial over E of alpha, will divide F because F satisfies alpha, okay, and mu alpha is minimal polynomial, so mu alpha will divide F. Now since here from here what we have is that degree of mu alpha E is less than or equal to degree of F, but degree of F is given to be P, right? What we have, P, which is from here less than or equal to degree of mu alpha E, this is less than or equal to degree F, which is just P. This implies nothing but they are all equal. So in fact, F will be, because F is exactly equal to some C, might be because degrees are same and mu alpha is irreducible. So mu alpha E into some C, where C belongs to E C is a constant, degree 0 over E. Okay, so this implies, after all, uh, mu alpha is irreducible, since now since mu alpha is irreducible, by definition we have chosen irreducible mu alpha, irreducible polynomial, irreducible. This implies f is also irreducible. Okay, so good. So one part is done, right? We wanted to show fx is also irreducible over E. Now we want to prove other side. So because f is irreducible, okay, let's see other side how to solve this. Assuming f is irreducible over E. Okay, then let's see. We have this extension kf, then E, then here we have k. So f is irreducible. This is also a splitting field over E of f. Now, if we use, uh, I'm just using hint. The idea proved here, 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 here. I'm just pointing out here. Okay, I'm just pointing out here. So n roots are generated. N roots are generators of k of degree of, here it is generated by p roots of f. This is nothing but uh, k x1 x2 xp, p roots. So total degree of extension, this k f over k, this is less than or equal to p factorial, right? Just using the trick in 12.13, sorry, 3. Okay, if now if p divides the p divides this degree of extension e over k, what happens? And this degree of extension divides further kf over k, so biggest degree of extension, right? So p should divide. Okay, so here we are like this. Oh. Oh, we are not using this part. F is irreducible over E. Otherwise, half of the problem is solved, right? What I'm going to do is this. Let me don't write it here. Okay, so we all have this in our mind. Now, if possible, we assume. Okay, if possible, let me change the color so that this is important. Pause step. If possible, let P divides E over K. This degree of extension. Then, okay, not there. I want to write, uh, if possible, let P divide this, and now consider alpha in V K F. Okay, some root of F, some root which is not in, of course, not in E. Of course, alpha does not belongs to E, since F is irreducible over E. And then what I'm going to write here, K E, sorry, K E E alpha, which is inside KF. So for this field extensions, we write degree formula. Okay. Degree of KF, sorry. Okay, not, I should write in bracket only. Degree of KF over K. This can be written as KF over E alpha into E alpha over E to E over K. And this is less than or equal to P factorial is fine. Okay. Since we have n distinct root, uh, since cardinality of VF is exactly P, okay, so any permutation of roots will give you an automorphism of KF, K automorphism. So this will be bigger than P factorial or cardinality of SP. Any permutation of roots of F in KF defines a unique automorphism. Field automorphism. Okay. We are defining on the roots of F, but we will extend them algebraically over all of Kf. Okay. So any automorphism will give an uh, any permutation gives an automorphism. So I want to directly write that these are all equal. Okay. Anyway, from here what we have is the next step. This is p factorial into kf over e alpha. Sorry, e alpha into this is p e over k. E alpha over e. This is py because this is equal to degree of f. F is irreducible and f is minimal for polynomial for alpha, right? And this is equal to p. That is why. So this implies so here we have that now p is gone. You see e over k into kf over e alpha is equal to p minus 1 factorial. Okay, so all the factors of either e over k or k of over e alpha, they are coming from p minus 1 factorial, right? So this implies p does not divide e over k. E cannot be p cannot be obtained as a factor, okay, in p minus 1 factorial because p is prime. So using that, okay, in some cases it may happen that we can get the largest thing, that like 6 factorial if you had initially, and even if 6 is cancelled, then 2 into 3 will will give you a 6 inside this, and that 6 can be happening, that this might be 6 or divisible by 6 like that. But here because p is prime and p is gone from this product, okay, from this product, so now p is never going to happen as a factor of this or even obtained as a product sub product in this big product, okay, p minus 1 factorial, because p is prime, so never can it can never be happen like this might be divisible by p. Okay, anyway, so this is how to solve this part. uh, okay, so what next we have is this. So I started late today. I was waiting if someone is joining or not. No one joined. So I will stop early. It is about an hour. I started. Let's see next question. KB characteristic not equal to 2 field. Kx be function field in one variable and L be this. Okay. So that 1 plus kx does not belongs to this and 1 minus kx does not belongs to that. One only this is enough. Similarly, other thing will follow. So it is enough to show root 1 plus x does not belongs to k x. I'm writing this as small x, okay? So this is my variable. Don't assume that this is some element. This is variable. I'm just taking it as small x. If something is needed, I will not use this small x in this question. Okay, so belongs to, does not belong to 1 minus x. So we will follow the hint and solve this. Okay. So first of all, they want to observe that this is simple transcendental extension over K. Okay. So you just see this. This is nothing but K. Okay. Let me write in the next line so that you understand it. Next time, whenever you see it. K x root 1 minus x. This is same as K root 1 minus x. Okay, this might not be looking trivial to you, but it is very simple. If you just see, uh, we just need to show this that x belongs to. Okay, this part is trivial. This part is we want to check, and that all that we need to check is x belongs to this side or not. So, but x can be written as x can be written as 1 minus or 1 minus x 1 plus x minus 1, right? And from here this can be to 1 minus 1 minus x. Okay, and that can be written as 1 minus 1 minus x whole square. Not like this. We're just very close to this. Uh, write a square root and then square it. Okay, so yeah, uh, this belongs to anyway k root 1 minus x. Okay, good. This equality follows first observation. Now next, uh, let y is equal to root 1 minus x. This is our simple extension. Uh, now, what 1 plus x satisfies some polynomial over ky. What is that polynomial? One plus x is equal to 1 plus x two plus x minus 1. This is nothing but 2 minus 1 minus x, and this is nothing but 2 minus y square, because y square is 1 minus x. So what we have here, and 1 plus x we want to get some polynomial in one. Okay, so here we can, this can be written as 1 plus x square root and then square. This implies z square plus y square minus 2 not equal to 0. This is the polynomial in k, y, z, which this is the polynomial which okay, so is this the minimal polynomial or square root of 1 plus x, and square root of 1 plus x belongs in ky or not? That is not clear, huh? So what to do here is that now this polynomial fz, if let's say py by qy belonging to ky be any root of fz in ky, then py by qy square minus plus y square minus 2, this is equal to 0. From here, at least this is clear that qy should be 1. We have chosen p and q co-prime. Phi is transcendental. Okay, so this is polynomial ring. So round bracket, square bracket, they are different. Now y square minus 2 is not square. That is why we have chosen characteristic not equal to 2. Okay, characteristic k not equal to 2 implies y square minus 2 is not a square, not a square in ky. This implies neither y square minus 2 or 2 minus y square, doesn't matter. But this implies that no such p and q exists. That is all. So 1 plus x or 1 minus x. What was this? Yeah, 1 plus x. square root of 1 plus x, which is root of is root of f. So 1 plus x does not belongs to ky. So that part is also done. And, yeah. So let's see next question maybe. L over kx be normal and separable field extension. Determine the degree of field extension L over kx. So that okay, so first we have to show that this is separable and normal field extension. Oh, okay. So this is first of all, let me write this diagram first. What are involved fields? Here we have L, which is k x root 1 plus x root 1 minus x. This is given in first line. Okay. And here we have k x 1 plus x, and then we have k. One more field extension we have k x 1 minus x. Okay. So we have a common field extension kx here, and then we have k here. I'm just writing this diagram. There are more way to do this. Okay, we can just directly write k attached with root 1 plus x like that. So in this diagram is helpful to us for determine the degree of L over kx. We want to degree this degree, and this is normal and separable field extension also. Good. Composition of Galois field extension is again Galois field extension, right? To let's say this is our x1, this is x2, mu x1, and this is our base field kx. What is this? X1 is square. Okay, let's say variable is t, then t square minus x minus 1. What is mu x2 kx t? This is t square plus x1 minus 1. Okay. Note that these are constant. They are lying in the base field. So no worry about that. So now we have got two minimal polynomials. So the degree of field extension, at least here, this is 2, which is degree of mu x1, and since x2 does not belongs here, this is 2. Since x2 is outside, mu x2, degree mu x2 is, oh, this is getting messy, which is degree, and that x2 does not belongs to, let's say, let me also denote this notation. This is, let's say, L1, this is L2. Good. So this is why we have L over K degree extension. Total we have L over K 4-degree extension. And now we want to check what is automorphism group of L over K. Okay, so T square, so those two distinct, since mu x1 and mu x2, mu x1 and mu x2 are distinct, irreducible, and separable. Yeah, separable, we are assuming that characteristic not equal to 2 and maybe characteristic 0. Yeah, characteristic not equal to 2 is enough, because +1 and -1 in that case they are different. So this is they are separable, irreducible and separable. So F is equal to mu x1 into mu x2. L is a splitting field. And whenever we have a splitting field for separable polynomial, so now the thing is done almost. Splitting fields of separable polynomial are Galois field extension, or separable and normal extension. Normal and separable. What is, and its Galois group L over Kx. So Galois group correspond to these two things. Roots of mu x1 will go permute the roots. So we have two roots for mu x1, two roots for mu x2, and they are only and any automorphism will, as any kx automorphism is defined by where it sends roots of f. So what happens here? The roots of mu x1 goes to roots of mu xi. I should write roots of mu xi. So this is true for any case. So in this case, we know that what is Galois group going to be. This will be L over kx 4 order group, right? Because degree of extension is 4 also, and in this case, it is factorization is 2 degree polynomials. So this is Z2 cross Z2 isomorphic to, I'm just saying. And now further discuss the action of Galois group. L over kx on the zeros of V and Gy, where Gy is polynomial of kx with the splitting field L over kx. L over kx, we have a splitting field of Gy where some polynomial. How the Galois group is acting on zeros of Gy. So this question is mostly discussed in the class, so I'm leaving it. Okay, I don't want to write this in details, and the time is getting up now. I started late because I was waiting if someone is coming or not. As usual, no one came, so it's now about 6:25. So let's see if I can do more. So that L over kx is separable normal field extension. Determine the degree L over kx square and its Galois group L over kx square. Furthermore, the action of Galois group is on 0 of hy, where 0 is polynomial of kx square with a splitting field L. So we have many more questions. Actually, I'm getting tired if I should do or not. Let me. But I can just give some hint in this question at least. Uh, these questions are simple if you just let's, for example, let me do this one and then I will leave. Next question. You might have already done these questions, so solve them. That will be fun by solving by yourself. L over kx square is separable in normal field extension. Just look into this kx over kx square. This is 2-degree extension, right? Mu x kx square t with t variable. This is nothing but t minus x square. T square minus x square. So this implies that the degree of extension is 2. And 2-degree extensions or 2-degree extensions are because since characteristic k is other than 2, not equal to 2, this implies this will be separable. Okay, this is separable field extension because it is a splitting field of this plus x minus x will be the root of this polynomial mu x. Okay, and plus x minus x both are distinct, so this is irreducible polynomial, which is irreducible in here, which is separable. So this is separable field extension. In fact, this is Galois field extension. This implies kx over kx square is normal and separable. What I just told is, since it is a splitting field of, since it is, let's say, a splitting field, and this is irreducible and separable over kx square. That is why this splitting field is normal and separable. But separable field extension under composition, they are separable again, and same thing for normal. So that's all is this. So Galois group, how to calculate Galois group now? So actually, I'm tired and now I don't want to solve this. Okay, so if you have doubts, you can ask through the comments. I will some other day provide you solution, or you just ask me through the comments. Huh? I'm leaving this. Uh, hope for best wishes for your exams. Okay, and enjoy these left questions solved by yourself, and let me know if you can't do. I'll try to upload later. Okay, so bye bye.